Okay, so this is the briefing video for the Grignard experiment. And so I'll start by just going through the reaction scheme that shows you what you're actually going to be doing. And then I'm just going to talk through some of the reasons behind how some of the key skills kind of work. So the distillation under reduced pressure and gas chromatography will be some of the new skills that you'll be sort of learning in this experiment. But this experiment also gives you a lot of practice of sort of, doing what is a relatively tricky reaction. You've got to be able to add the reagents carefully, liquid-liquid extraction, and a kind of atmospheric distillation as well. Okay, so you will have learnt before on the course how Grignard reagents are really sort of important nucleophiles in organic chemistry, and how we use them to sort of attack carbonyl groups to make carbon-carbon bonds, and that's what's happening here. But Grignard reagents are also good examples of how in organic synthesis, things that are good at reacting are also not very stable. So often when we're performing these types of reactions, what we've got to do is we've got to prepare the reactive reagent that we want to use, and then we've got to use it straight away in our reaction. They don't sort of, we can't store them in bottles or buy them from commercial suppliers to use them because they're just too reactive. So that's what you're doing here in this experiment. The process is going to be that you start with 1-bromobutane, and then you're going to mix it with magnesium turnings, and you're going to make your Grignard reagent. So this Grignard reagent is reactive, and so we want to make sure that it reacts with a ketone, and it sort of, if it does that, then you should get your product in good yield. We want to but we've also got controls in place to make sure it doesn't sort of react with moisture in the air, because if it reacts, the Grignard reagent reacts with water, well then it's not going to react with the ketone, and then you're going to get lower yields in your reaction. So we've got measures in place such as using dry glassware, using calcium chloride guard tubes, using dry solvents in place to ensure that you can make a good amount of Grignard reagent, and that it's going to be stable and not decompose in the presence of water. Once you've got your Grignard reagent made, then you're going to add in your methyl to pentan 2-one, your ketone, to actually react with the Grignard. It will attack as a nucleophile onto this carbon, making this sort of portion, this part of the carbon chain of the molecule, and giving you an alcohol sort of by the alcohol product. Again, one of the other features of using really reactive reagents is if you're using reactive reagents that sometimes you have to add chemicals together slowly, so that we don't get reactions that sort of become too vigorous and too hazardous. And so the process of making a Grignard is quite exothermic. And so what will happen is you'll start with magnesium turnings in your reaction flask. You'll add bromobutane to it quite slowly to gently form your Grignard at a steady rate. But also when you add your ketone later in the reaction, you'll also be adding that slowly in a dropwise manner to make sure that can react at a nice steady rate with your reactive Grignard reagent. And so the setup of the reaction is complicated. You've got multi-net flasks, and so you can attach a dropping funnel to be able to add these reagents in a dropwise manner. Okay, so that's how you sort of run the reaction to make your product. And like I said, hopefully if you run this under nice dry conditions, you will react most, if not all, of your ketone to make your product. But if your reaction is wet, or you don't make enough Grignard reagent, then you're going to have quite a lot of the ketone left over and a lower yield of your product. So at the end of the reaction, there'll be a liquid-liquid extraction, and that will include the workup where you protonate the magnesium salt to give you the alcohol at the end. And then the product that you're trying to distill is a liquid, so you can do a distillation, but it has a very high boiling point. And so if you distill this under sort of atmospheric pressure, it will boil around 200 degrees. At that high temperature, the product can actually decompose as well. So instead, you're going to do a distillation under a reduced pressure, and I'll explain how this works in more detail, but that will allow you to distill your alcohol at a much lower temperature where it won't decompose. Also, your distillation is going to be more complicated because I've said there's a chance that you could have unreacted ketone left. Well, this has a lower boiling point than your product, so your distillation will be a little bit more complicated. It will show you how to distill and separate more than one liquid as well. And then after you've done your reduced pressure distillation, you're also going to take some of your sample, but very importantly, not all of it, and you're going to take some of it and distill it under atmospheric pressure. And through the atmospheric distillation, you will actually see how it decomposes, what it would decompose into. And then with gas chromatography, this is a technique that you can use to analyze oils to work out what you've got, and in particular how many things that you have. It will be able to show you if this compound does decompose and what it decomposes into as well. So I'll also explain how gas chromatography works and how it will work in regards to what you're looking for from the gas chromatograph from your experiment. Okay, so do watch the pre-lab videos to learn how to perform these techniques. So we've got a video showing you how to set up the Grignard experiment. You can see it's one of the more complicated setups that you will have done thus far in your training, and also for a reduced pressure distillation as well, which is a lot of similarities to distillation, but there are more complicated parts to it as well. As you can see, just a part of the picture here, there are more sort of flasks and a new type of adapter as well. Okay, so I think I've explained a lot of what you're doing in the Grignard experiment already, about how you're preparing the Grignard and then adding your Grignard reagent. So I'm just going to re-emphasize some points. Do make sure your glassware is dry before you use it, otherwise it's going to decompose the Grignard reagent. Also, to make sure that you are making the Grignard, you should see some bubbling forming, and this is because it's got it's an exothermic reaction that will start bubbling your diethyl ether solvent, which has a low, really low boiling point. But you want to see gentle bubbling of your Grignard reagent. If you add your bromobutane really quickly, okay, then what can happen is the ether sort of bubbles too vigorously, and you can get your mixture coming out through the top of your condenser as well. Okay, so there's going to be a balance here between, you need to sort of maybe sometimes just use your hands to warm the flask, so you get gentle initiation and formation of your Grignard reagent. But you will also have an ice bath on standby underneath your flask if you feel that the reaction is getting out of control. Okay, before it sort of goes out through the top of the condenser, you can sort of put it into the ice bath. You know, stop the addition of your bromobutane, cool it down in the ice bath, and get that and slow down the rate of Grignard formation. Okay, you may have to do is you may have to go through a process of initiating your reaction, warming it with your hands, getting the Grignard forming, and then cooling it down, and then maybe warming again, cooling it down, if you're struggling to get a nice steady control for forming the Grignard reagent. Okay, and so this is about the reduced pressure distillation. So as I mentioned, you're doing this because your compound decomposes at higher temperatures, and so you know, the relationship between pressure and temperature is if you lower the pressure, you can lower the boiling points of liquids. And what you need to have to do this particular distillation is you will attach your distillation apparatus to the vacuum pump in your fume hood, and in your fume hood there will be a manometer which will tell you the pressure reading of your distillation apparatus. This pressure must be below 30 millimeters. If your pressure isn't low enough, then then your products will be distilling at a temperature that's too high, and where you'll see decomposition. Okay, so it's really important that before you actually start your distillation, you check that your vacuum pump is going to give you a pressure that's low enough. If it's not, then you may have to go into another fume hood that's got a better vacuum to be able to do this distillation. There's also unique pieces of kit like a Kleisen flask, a capillary leak, and a pig adapter. Okay, and these pieces of equipment you'll get from stores. The reason you're using a pig adapter is links to what I said before, where you might have some starting ketone left over in the distillation. And so what you can do with a pig adapter is you can attach more than one flask at the end of your distillation. So you can rotate the pig so that any ketone that you see coming off will come off first into the first flask, and then when you see a rise in temperature, okay, you know that it will be something else, and that should be a product. You can rotate the adapter so then it collects in your second flask, and if you see any further jumps in temperature, you can rotate again to collect in your third flask. Okay, so the pig adapter allows you to collect you know, more than one liquid. So it's really important that you use a thermometer to monitor the distillation, to work out, you know, what your, you know, when, you know, how, you know, what's coming off your distillation, how many different things there are, and when is the right time to sort of turn your flask. You want to be turning it at the appropriate times to sort of make sure that you don't, you know, you've fully separated starting material and product, and also that you've got as much yield as you can get out as well. Okay, and as I mentioned before, after you've done that, then you'll take some of your product, you'll add a little bit of acid to it, and then you'll do an atmospheric distillation. This will be set up in the same way that you've done a distillation last year, and this will show you how the product would decompose and why you had to do you know, do this more complicated reduced pressure distillation. And gas chromatography will tell you how what the compound is decomposed into. So this is how gas chromatography works. Okay, it's an analytical technique that's used to tell you what you've got and how many different things you've got if you've got like a mixture of different compounds. Okay, so at the end of both your distillations, you will have your samples, hopefully from the reduced pressure distillation, a pure sample. So through gas chromatography, we should see like one nice clean peak that corresponds to your product. From the decomposition sample, you should see, possibly, it's certainly a different peak, but possibly like more than one peak. You might have some starting material left over, as product, sorry, but you might have some decomposition formation as well. And so the way that gas chromatography works, like all chromatography, you have two phases, okay, a stationary phase and a mobile phase. So in gas chromatography, the stationary phase is a column with usually solid with silica. So that's similar to thin layer chromatography, for example, where the stationary phase is also with silica. And then you've got a mobile phase, which is gas. And so your samples at the end of the experiments are liquids, but what will happen is they'll get injected into the machine and they will be vaporized into a gas. And then you'll also have a carrier gas, which will help your samples flow through the column. And the principle of gas chromatography is the same as other types of chromatography. Okay, if you've got something that's non-polar, it will have weak interactions with the column, so it will travel fast through the column to reach the end of the column and reach the detector. If you've got polar compounds, it will travel more slowly through the column. So what should happen is if you've got more than one thing in your sample, the non-polar material will reach the detector first, and the detector will usually have something like a UV detector that will measure the UV absorbance of your compounds, and that will give you the first peak at the first retention time, the quickest retention time, to show you the first compound that's come off, and the size of the peak will tell you how much was present of that first compound. Then the more polar compounds will come off next, and when they reach the detector, you will see future peaks coming off. Again, the size of the peak will be related to how much of that sample what was present. Okay, so if you've got a pure sample, you should see from your chromatograph one peak with a particular retention time. If you've got lots of different samples, if you've got lots of different compounds in your mixture, then you should see, you'll see lots of different peaks in your chromatograph. So it would look something like this. Okay, so the non-polar compounds come off first. They've got the shortest retention times. The more polar compounds come off later. And the size of the peaks will give you an indication of how much was present in your sample. So we can see here in this sample, there's sort of 4 different compounds where there's quite significant amounts in the sample, but then there's one particular compound which there isn't a lot, and there's a very small peak. So you'll see this in your gas chromatography chromatograph that you sort of run for your experiment. What you need to be looking for is, how many peaks do you have in your chromatograph? That gives you an indication of how many things were in both samples. You'll be looking for things like the starting material, ketone, the product, and the decomposition sample as well. And then you'll be looking at the retention times of those peaks as well, and matching those up to standards. Okay, so we've run standards where we sort of know what the starting material peak should come. We know what the product peak should come, and same with the decomposition sample. So that's what you need to be looking for in terms of analysing your chromatograph, and kind of need to comment on in terms of your analysis. Okay, finally, this is just a kind of overview of how long things should take for your experiment. Essentially, it's a 1.5 day experiment. So the morning session will be spent of your first day, should be spent sort of setting up and running the reaction. The afternoon would be, doing your sort of liquid extraction. And then both stages of the distillations take, a couple of hours. So you may be able to get the reduced pressure done on the same day. You can maybe doing it on the second day. Just make sure you're working a pace that suits you. But all in all, it should take about 1.5 days. Okay, so that's the theory. That's the the overview of the Grignard experiment.